Okay, welcome back, everyone, for the last session of the conference, with our final keynote talk by Professor Rich Sutton from University of Alberta. It is an honor to introduce Professor Rich Sutton, which is a distinguished research scientist at DeepMind, a professor in the Department of Computing Science at the University of Alberta, and a fellow of the Royal Society UK, Royal Society of Canada, a.k.a. Alberta Machine Intelligence Institute, or AMI, and CFAR. He received a PhD in computer science from the University of Massachusetts in 1984 and a BA in psychology from Stanford University in 1978. So prior to joining the University of Alberta, he worked in industry at AT&T Labs and GTE Labs and in academia at the University of Massachusetts. In Alberta, he founded the Reinforcement Learning and Artificial Intelligence Lab, which now consists of several principal investigators and about 100 people together. He joined DeepMind in 2017 to co-found their first satellite research lab in Alberta. Sutton's research interests center on the learning problems facing a decision-making agent interacting with its environment, which he sees as central to intelligence. He has additional interest in animal learning psychology, in connectionist networks, and generally in systems that continually improve their representations and model of the world, which is exactly the topic of this conference. So he's also the co-author of the famous reinforcement learning textbook, which I think most of us have read at some time, and which has done several foundational work in reinforcement learning. So today he's going to talk about maintaining plasticity in deep continual learning, and this is a joint presentation with Rich's graduate student, Sibansh Dohar. So let's welcome both Rich and Sibansh for this keynote talk.
Thank you very much, Sarath, and the other organizers for inviting me. It's a great pleasure and honor to speak to this group, this special group, this community that's forming. This is a little bit not maybe a standard keynote talk. It's actually a bunch of new work that we're doing, that Sibansh is doing, and Fernandez Garcia and Parash Raman. And Rupam Mahmood and I are also participating in that. Yeah, so I particularly wanted Sibansh to have a chance to talk today about the work that he's played such an important role in. And it's work that I'm really excited about. It's funny that it's not going to be about reinforcement learning. You probably associate me with reinforcement learning. I'm going to be talking all day about supervised learning. And because the problem of continual learning is present in both settings, and why not study it in the simplest setting first? So we're going to talk about deep learning, whether it can really work for continual problems, is a question we all care about. And to make sure the main message gets across, I'm going to do it first, make sure it's clear. Basically, I'm going to argue that deep learning doesn't really work for continual learning. And by not work, I mean that the learning slows down and eventually it's going very, very slowly, similar to that of a non-deep, just a linear network. And by deep learning, I mean the standard methods that are specialized, as they all are in deep learning, to work in this one-time learning as opposed to continual learning. And perhaps a limitation of what I'm going to argue today is that I'm not really going to consider replay buffers, because I consider them, well, a very inelegant algorithm, and so much so that they themselves are an acknowledgement that deep learning doesn't work without such extreme measures. Anyway, it's a limitation of what we'll present today. Okay, so instead, we have to find better learning algorithms, and ones which will work on continual learning. And it's not our second theme is that it's not really that hard to improve the methods, and then we can do deep learning like things for continual problems. We just have to choose to do it. We have to start looking for such methods, and we have to get out of the rut that one-time learning has put us in. Okay, so that's the message, and it's not entirely a new message. There are earlier indications of these problems with deep continual learning. We know about catastrophic forgetting from the 90s, and also in those early days, there was a lot of work in the psychology, cognitive science literature about loss of plasticity. And more recently, The Ash and Adams result has been influential, where they showed that warm starting doesn't work. What is warm starting? It's you present with some of the data, and that warms the system up so that it can do well on subsequent stuff. And they find that it just doesn't work. That if you warm it up, it actually does worse on when you present the new stuff, and it's better just to throw away whatever you initially learned and do the whole data set together in one-time learning fashion. Another bit of new work on primacy bias and deep reinforcement learning, where they show that if you do some reinforcement learning, often it's a good thing just to throw away everything the network has learned, and retaining the replay buffer, but you throw away everything the network has learned and have it learn again from scratch. And that way you can keep learning. And to me, it's just this kind of resetting the network is just a patent evidence that the continual deep learning is not working, and we've had to resort to such extreme things. Finally, not yet, I guess, no, it's just come out in iClear, the capacity loss paper. It's by Clara Lyle and others, including Will Dabney. Capacity loss is another name for the loss of the ability to learn. And so we're going to call that plasticity loss. So no one has really done a direct test try to test or demonstrate the loss of plasticity in supervised learning. And that's kind of surprising, but that's what we're going to do today. Now, you know, this language, a lot of these words are a little bit redundant. I just want you to become comfortable with the way we're using them. By plasticity, I just mean the ability to learn. And so if you've lost plasticity, you've lost the ability to learn. That means you can't do continual learning. And maintaining plasticity means you maintain the ability to learn. And that's what we should be, of course, interested in as learning systems. We want to have the ability to learn and keep doing it. And at CoLLAs in particular, we should prioritize this maintenance of plasticity, continuing to learn. Okay, so what we're going to have is we're going to have demonstrations of loss of plasticity in continualized versions of ImageNet, classic problems like ImageNet, MNIST, and generic regression. And we're going to try to understand that. We're going to look at, you know, whether somewhat more sophisticated methods from the deep learning literature can maintain plasticity. And then I'll turn things over to Shubhansh, and he'll talk about our simple little idea for extending backprop so it can fully maintain plasticity. That's the plan. Let's get started with a demonstration. And how would we make a demonstration of continual learning, or a demonstration that deep learning doesn't succeed at continual learning? We need a test, and we could use a single non-stationary task. That would be one way. Another way would be to have a sequence of different tasks with no indication to the learner that there's been a change. And it could be a reinforcement learning tasks, but you know, that involves all kinds of additional things, and we want to keep things straightforward so we can know what's going on. Deep learning is complicated enough. So it could be supervised, I think, and these are the choices that we're going to do. We're going to do the sequence of tasks, and we're going to do classic classification, and we're going to do some classic deep learning data sets like ImageNet and MNIST. So let's talk about ImageNet. ImageNet is a data set with millions of images labeled by nouns. Standardly, there's 1,000 classes each with 700 or more images, and it's widely used to learn classification. They can image and predict the class. Here's a nice picture of a shark, but it's downsampled to 32 by 32, and that's a reduced data set that we're going to use, a reduced version of ImageNet, a standard reduced version. And the idea of this experiment is to have a minimal change from deep learning practice. Okay, so we're going to have each of the 1,000 classes with its 700 images, we're going to break that into 600 training examples and 100 test examples. And then we'll take the classes in pairs to produce a sequence of 500, because there's 1,000 altogether, but we put them in pairs of 500, a binary classification task. So we might start with class 1 versus class 2, and we train on that, and then we do class 3 versus class 4. Of course, it's all shuffled across runs and randomized. Now, within each pair, within each task, binary classification task, we have 1,200 examples because there's 2 classes and they each have 600 examples. And then there'll be 200 test examples because there's 100 for each class. So we'll do those 200 test examples, and that's how we'll measure performance. And then we'll proceed right into the next pair, the next binary classification task. We'll measure performance, percent correct on the test set by argmax, and we'll average over many runs. We'll vary all the things that you should vary. Okay, so that's the problem. Now I need to talk about the network, the solution. So the network for ImageNet, we're going to have these 500 classification tasks. We're going to apply them all to the same network. There's something that maybe isn't the best, but what we chose to do here is we did reset the heads at the task switch. We'll not do that later, but we do it here to make it, to remove that complication. And otherwise it's a standard network. I guess it is a standard network. It's a little bit narrow for ImageNet because we only have 2 classes. Usually they have all 1,000 classes. Well, we have 3 convolution layers of filters, and then we have 3 fully interconnected layers. Their widths are 128 units, and 2 heads. And then for each task, we make batches of 100 examples, 12 of them, because there's 1,200 examples, remember, in a task. And then that batch, we would train to for a while, and then we go through all 12 batches, and we do multiple passes through the data, 250 epochs. And the initialization is the standard way, but it's done only once before the first task. And we're using stochastic gradient descent with momentum, cross entropy loss, ReLU activations. And then, there are many variations possible, and we've explored many variations. We're going to show you some representative results. And I want you to ask these questions. How do you think performance will evolve over the sequence of tasks? Like the first task and the second task. Will it be better on the first task, or will it be better on the second task? This is a Zoom talk, and I can't really interactively get your answers, but think for yourself, decide for yourself, which do you think will do better? Will the initial task be better, or will the second task benefit from the experience on the first task and be better? And then, what about the 500th task? Should it be, really well? Okay, so here's the initial performance. The initial performance, and this is, and the answer is it's mixed. Okay, it depends on the step size the backprop is using. So now you're going to see a lot of graphs today, and we should start getting used to them. And so I'm going to go through a little bit slowly. We here see performance as percent correct on the test set here at the end of each task in ImageNet, averaged over some number of runs, versus the task number. So this is the pairing, the binary classification problem. So like for this step size, 0.01, backprop got 89%, whereas chance is 50% because it's a binary classification. So over that first task, it was long enough, or you did well by the end of training on it. And but for different step size, you might have a lower thing. But with this slower step size, you actually did get a benefit. So you did certain well on the first task, and the second task you did better, and the third task you did still better, topping out at about the 5th task. And then there's the question, in the long run, these seem to be trending down. But what happens in the long run? Oh, this is reminding me to tell you that the shaded region is one standard area, so these differences are not significant. This difference is significant. And the linear baseline is the performance of just a linear head directly from the pixels. So you really should be doing better than this, or you're not doing deep learning. Okay, so the conclusion is learning rate plasticity improves sometimes over the early tasks, but in the long run, what happens? So in the long run, this is what happens. So this is the same kind of graph, but now we're going from 1 actually to 2,000 tasks. And it's also in bins of 50 to reduce the variance. So each data point is 50 tasks averaged. So like the very first data point, remember, there was at 89. But once we average over the first 50, it comes down already. Okay, now we see, we've also added one more line for a still slower version of backprop. But we look at the red line, which had been doing well, and we see it's just going down and down with more tasks. We are losing plasticity. We are actually below the level of a linear network. If we have a slower backprop uses a slower step size, we also lose plasticity dramatically, just a little better than a linear network. And making it still slower doesn't help it either. We're at this low level. Okay, so what do we conclude? Well, first we have to remember, well, for good hyperparameters, plasticity decreases across tasks. We have loss of plasticity, nearing the performance level of the one-layer linear network or worse. So I think it's fair to call this, at least the red line, catastrophic loss of plasticity. Now, the proviso is that, I'm claiming this is representative, but the details does depend on the numerical details of the choices here. And each line actually takes 24 hours of human time on multiple processors to compute. And so it's not really practical for doing systematic experiments. So now we're going to shift to MNIST, where we can do much more thorough systematic experiments. And it's also a classic task, it's just a bit smaller. So MNIST is a data set with 60,000 handwritten digits, so like this. The images, they're numerals, handwritten numerals. So the classes are 0 to 9, and they're grayscale 28 by 28 pixels. That's the data set as delivered. And then we're going to use this trick that we didn't invent, but it's permutation, where we make a new task, because this is like one task, classify these 60,000 images into 10 classes. And we can make a new task by shuffling or permuting the pixels. So this is an example of a permuted image. This is actually the numeral 1 after being permuted. And this trick comes from these fellows. It's been around for a little while. And so it's a way of generating a whole sequence, an arbitrary number of permuted tasks. For every permutation, it's a different task. So we'll do one permutation and then we'll do another. And in each one of those tasks, we'll do all 60,000 images, permuted images. There'll be no indication of the new task. The weights will be initialized once before the first task. And one thing that's really nice about this problem is we're going to switch to the natural performance measure for continual learning, which is the online performance measure. So we're going to do online cross entropy loss. So that's the problem. Now I have to describe the network. The network is a sort of normal network. It has 4 fully interconnected layers. The main ones are with 2,000 units. And then there's 10 units at the end. And you notice we're not doing any convolution here. And this is fairly normal in MNIST. The convolution is less important. The images are centered and scaled. So it's pretty normal. You can, I think, do a little better if you use convolution, but it's not a big deal. It's common to do it in this way. It's not uncommon to do permutations. Okay, so all networks use this, all the classification tasks use the same network. There's no indication at all of task change, and we initialize in the same way, but only once, of course, beginning before the first task, and then we use stochastic gradient descent. We're not even using momentum. Momentum isn't really helpful in this problem, and ReLU activations. Okay, so now we're ready for the results, and if you look at online performance, so yeah, you want to get used to this too. Online performance. Or actually, I guess this whole slide is to get you used to it. And here we're just showing, the actual online performance example by example. This is averaged over 30 runs. And because we have a task change, think about it. I mean, you'll get 60,000 examples, and at the beginning, you'll be guessing 1 out of 10 at random. And so your starting performance will be 10%. And then you'll start to figure out this permutation, and you'll perform well. And then there'll be a task switch, and you'll be dropped back to 10% performance level. So that's what this dramatic drop is. And this is the way a lot of sequential continual learning graphs go. They go up and down. And I've been calling them alligator graphs because they're like an alligator's tail with these spikes and then the drops. Anyway, I call them alligator graph. That's a meme I'm trying to promote. So let's look over here now, because here, we wonder over time, are things getting better? And one thing to do is just say, well, is this spike better than that spike? And so this graph lines up the spikes so that they all begin at 0. This is the example number within the task. So the first task is this blue line, and then the 10th task is the top line. So you actually do better on the 10th task. And you're starting to fade by the 100th task, and by the 800th task, you're doing worse than the first one. Okay, so that gives you a little bit of a picture of what's going on. The way we're going to show in the rest of the talk, we're going to not show the spikes. We're going to show the average performance over the spike. So we'll reduce a spike to a single number. And so it'll be like these blue points. And then you can see, so here you see, it's clear that performance is improving somewhat at the beginning, and then it's leveling off. What happens in the long run? So we can see improvement over early tasks, but there's degradation by the 800th task. We're not doing very well. So let's look now at the long-term performance. That's what this graph here is. We're showing for various step sizes. We're looking at the same online performance measure. We just have the one dot, and this red line is the exact same run that you have previously seen the beginning of. In the long run, it does go down, steadily down, and even by 800 tasks, it's still going down. So that's substantial loss of plasticity. And we see the same thing. If you have a faster learning rate, you come up faster, and then you lose plasticity faster. And even if you go slowly, you have the same arc. So there's substantial loss of plasticity at all step sizes. Also in network size. And now we're changing the network. We're changing the width of the network, the number of hidden units in the hidden layers. Instead of 2,000, they might have 10,000 units. And then everything is slower. There's much less loss of plasticity because the network is bigger. There's going to be more left. And but it's still going down. And if a small network, it really drops off. Okay, so larger networks lose plasticity more slowly, but they still lose plasticity. Now we're going to look. This is the second group of graphs that you're going to see. Most of them are like the one I just showed you: performance versus task number. But now we're going to look inside the network and try to understand what's going on. And this is small enough that we can start to do this. So here we're still are showing task number on the x-axis, but we're going to show different things. So this is the percent dead units in the network. And a dead unit is a unit whose output is 0 and whose gradient is 0. It's always 0. It's not like it's like a 0. Sometimes that'd be fine. But if you're always 0 and your gradient's always 0, you are dead. You're no longer participating in the plasticity of the network. And so this happens. If we just do backprop, so the same step size we saw it doing pretty well before, it's the number of dead units in the network that increases steadily over time, here up to about 20%, and varying with the step size. So that's an indication maybe of what's going on and why we have a loss of plasticity. Another thing that's been talked about, these ideas aren't looking for these things, isn't entirely new. was weight magnitude. You know, we're just, the weights are getting big and they're no longer able to change. The hidden units are not able to change and adapt and make good features for the new tasks. So if you just look at the size of the weights with backprop, they are steadily increasing over tasks. And so that could explain it. The weight's getting large, the units are overcommitted, become difficult to change. And the third thing that people have looked at is a notion of effective rank of the remaining hidden units. So now here we're looking at all of the layers, except for, of course, the last one. We're looking at all the hidden layers, and we're asking what's the rank of their variation? What's the linearly independent components of that, and how many dimensions does it have? And with backprop, the rank falls from about 40, goes up a little bit, then it falls to about 30. Not a very dramatic effect, but it is going down as we increase the number of tasks. So those are three things that we can look at and try to understand the loss of plasticity. And we're going to look at them as we go forward. Okay, so what's next? Yeah, now we're going to look at other methods other than ordinary backprop. And in fact, some of the methods do help and some methods don't. So this is performance on MNIST versus task number. So the red line is the line you've already seen, that backprop can do well and then it loses plasticity. This is step size 0.003 again. Okay, so some methods like L2 regularization is losing less plasticity. It's still losing plasticity, you know, it's going down, but it's losing less than backprop does. So what is L2 regularization? Basically, you're shrinking all the weights towards zero all the time. So it makes sense that would keep the weights a bit plastic, a bit able to change and not being overcommitted. Now, shrink and perturb is the same thing. It does L2 regularization, but it also adds random noise to the weights. So that increases diversity. And shrink and perturb does pretty good. It doesn't lose much or if any plasticity. Okay, so those methods are interesting. And some other ones we tried: online normalization. This is it's like batch normalization, but done online. We shift and scale all the signals, and that does do something nice at the beginning, but it suffers terribly from loss of plasticity with continual learning. And dropout has also been suggested as an antidote to the loss of plasticity, but it really does worse than backprop in this way. Dropout is where you take a fraction of units and you set them to zero in training, so that the network is forced to develop several features that are useful for each purpose. Okay, so now let's look in detail at these methods. Okay, let's do the same, understanding the loss of plasticity in these existing methods on MNIST, where these are the same three things, and the red line in each case is the backprop line. The backprop line at a good step size or representative step size. And we see all these methods, we can see how well they're used. So like, you notice one thing that stands out to me is that you get a lot of dead units with regularization, which makes sense. Like if you're shrinking your weights towards zero, then if they go all the way to zero, the output will be zero and the unit will be dead. So regularization puts you in danger of killing your units. Shrink and perturb, does shrink things, but also perturbs them. It adds random noise to the weights, and so it doesn't get as many dead units. So maybe it's doing well. Normalization looks like it's getting a lot of dead units. It's going in the wrong direction, and dropout as well going in the wrong direction. Weight magnitudes, well, one thing that you won't become as no surprise is that if you do L2 regularization, you can get weights of smaller magnitude, and shrink and perturb will also give you weights of smaller magnitude because it's driving for that. online normalization is getting large weights. And finally, effective rank. In terms of effective rank, remember you want to be high here. And so shrink and perturb and L2 are not really doing so well in terms of maintaining diversity. So it's still that's still a problem. Okay, and so that's what we can get by analyzing these methods. I want to mention another problem. I'm not really going to go through its results in detail, but all of our ideas and our algorithms, they've come from experiments on a still smaller problem, which we call slowly changing regression. It's an idealized problem, and you can do lots and lots of experiments on it because it's so small. And so I'm going to describe it to you, and then I'll skip over or go quickly through the results because they just confirm the things that we have already seen in larger scale problems in MNIST and ImageNet. Okay, so what is this problem? A slowly changing regression problem, a new idealized problem that targets continual learning. The idea is we're going to make a target function that's formed by a one hidden layer neural network with random weights and LTUs, linear threshold units, as their hidden units. So it looks like this. Its output is just the target is just a real number. So that's why it's a regression problem, right? We're not classifying, we're producing a number where we'd be interested in the squared error from the target. So, and now I'm just describing the problem. So this is how the target function is formed. It's linear in some hidden units, some hidden units. Those hidden units are linear threshold units. That means the activation function looks like this. And the weights between the final inputs are bits, random bits, basically. And the weights are random 0 or plus, they're all +1 or -1, chosen at random. So it's a very simple setup. One hidden units, all random weights, and that gives a target function. Then the special thing is that the input bits, and we treat mostly, these numbers can be anything. Here we have 100 threshold hidden units, and here we have 21 binary inputs. They can be anything. This is the case we use most often. Of the 21 bits, 1 is the constant 1. It's a bias input. And 5 of them are just IID flipping on every example, 50-50. And the other 15 are mostly constant. They're changing very slowly, like only every 10,000 steps, we pick one of the 15 at random and we flip it from +1, from 1 to 0 or 0 to 1. And that's the problem. The result is a slowly changing target function. It's slowly changing because as long as this doesn't change, we have this small function input output, but when it occasionally slowly changes, and so the target function changes when we add a new variation in the slowly changing bits. Now the learning network, all up to now I'm talking about the problem. The solution uses a learning network that has the same structure. In other words, one hidden unit, one hidden layer. It doesn't have LTUs, of course. It needs to be differential. But we only are going to have 5 hidden units. And so this means that the solution, the agent, if you will, is much smaller than the world, smaller than the target function. And so we can only approximate it. And so we learn an approximation, and then as the real world, as the target function changes, we will try to shift our approximation to follow it. And that's the problem. And with this problem, you can do lots and lots of experiments easily. And so then we were able to do very systematic experiments. And this, I'm not going to go through them, but this is the kind of things we can do. We can vary the step size thoroughly, and we can vary the activation functions. And like here, we're using tanh and sigmoids and ReLUs, all different possibilities. And then we can also do all the different algorithms with all the different step sizes and all the different activation functions. And we've also done atom versions of backprop and vary all the things, step sizes, activation functions, and then you can also make atom versions of like of all the other methods. Okay, so remember the message that I like to think that the empirical results I showed you today have supported and maybe showed more clearly than prior work that there's a strong sense in which deep learning just does not work for continual learning. By not work, I mean that as you get new problems, learning slows and eventually reaches a very slow level that doesn't really take advantage of the deepness. And by deep learning, I mean the standard methods. So these comments, it doesn't really apply. Maybe we can fix deep learning by making better learning algorithms that are specialized for continual learning. And our second message is that those are not too hard to find. And that's, well, I'll be turning over to Shivansh to give an instance of that. If we start looking for them, we'll get out of the rut that we have using one-time learning methods. Okay, so this is where we are in the talk. We're all set. I've covered the problem, and I hope we've established the problem. And now Shivansh will cover the extension that solves it in a significant sense. So let me just say a little bit. You know, I guess Shivansh Dohare, it's already been introduced a little bit. Actually, he's not one of my PhD students. He's one of Rupam Mahmood's PhD students. And he's one of the principals that are involved in this work. He's not the only one. I think we're all very excited where this is going. So Shivansh, please take it away. Shivansh is just going to share his screen so we can continue with the talk.
Okay, all working. Okay, thanks, Rich. So I'll be taking over the talk now, and I'll talk about our solution method, which we call continual backprop. To get to that, I'm going to first talk about the standard backprop algorithm, at least in the way it was introduced. And it had like two main parts. First was initialization with small random numbers, which was not repeated again, and then gradient descent at every time step. Now we need to think whether this is a good continual algorithm. But I would argue that it's not very well designed as a continual learning algorithm because it's doing a special computation at the beginning, which is to generate small random numbers to initialize the weights, but that's not being repeated again. Ideally, maybe we want some learning algorithm that does similar computations at all times. So the question is now, how can we make this algorithm more continual? What would be the simplest way to do it? So that's our algorithm, continual backprop with selective reinitialization. The simplest way to make backprop continual is probably just to reinitialize occasionally. Let's say after every few tasks, we can reinitialize the whole network, but that might not be ideal in a continual learning setting because that would mean that we are forgetting everything we have learned. It's probably not a good solution. The other thing we can do is we can initialize parts of the network. And if we are initializing parts of the network, it's better to initialize them selectively instead of just randomly reinitializing some things or some layers. We can just find units that are not useful and reinitialize them. For example, they can be dead units, or there can be a much more sophisticated notion of utility by which we rank which units we want to initialize. We find the lowest utility unit and then we reinitialize that. Okay, this idea is fairly simple and is a fairly straightforward extension of standard backpropagation and the standard way we do things. But it's also connected to this broader idea, which was introduced by Mahmood and Sutton, and they called it generate and test, where you simply generate units and test them for their utility. And these two ideas, this algorithm, continual backprop, forms a bridge between these two notions. However, their work was fairly limited to the setting where we had one incoming weight, one hidden layer and just one output unit. In this work, we'll extend this to the multi-layer setting and do a bunch of other extensions to make it work with deep learning and optimizers like Adam and things like that. Okay, so let's see this setup we have. We have a deep network where there is some hidden unit in the middle of it, and we want to find out how to extend Mahmoud's work. So first thing we have to do is we have to extend it to the general multi-layered setting where the fan out is greater than one. Fan out meaning there are more than one consumers to each unit. In the work, there was just one. So their notion of utility, which I previously mentioned, is used to find which are the least useful units. Their notion of utility was just to sum up the magnitudes of the weights, but because, their notion of utility was just the weight magnitude because there was just one weight. However, we have multiple weights. So the simplest generalization is to just have the summation over weight magnitudes. The other idea is to consider the activity of the features instead of just the outgoing weight. So we also multiply the sum of the weight magnitudes by the average feature activation. This is more important for modern activations like ReLUs and stuff, because there can be different scalings of the activation, average activation. But in their case, they were using LTU, so it was always 0 or 1, so it was not important. The next idea is to consider how labile or how plastic an individual feature is, like how fast can we change it. This is particularly important for our setup where we want to design algorithms that can keep learning and keep adapting fast. And finally, small change is we transfer the average contribution of this feature to the next consumer, to the bias of this consumer. This reduces the effect of this feature's removal. After doing all these things, we come up with this scary looking equation for utility. I won't have time to get into the details of this, but it's based on these 4 simple ideas. Yeah, you might also be thinking that this is somewhat limited. What about considering a global notion of utility? Like right now, the utility is only based on local components like input weights, output weights, and its activation. But ideally, we would want some notion of utility where we have a global measure, like how much does this unit affect the overall function that's being represented? What about that? And as I previously mentioned, this is also connected with this idea of generate and test, and that's a whole fully open field with lots of possibilities of improvement. And the one clear direction is to have better generators. Like here, we are obviously just re-initializing from the initial distribution, but it's tempting to think that there can be better ways to initialize than what we are doing right now that can significantly improve performance. Okay, so these are the algorithmic ideas that we improve. Now let's look at performance of continual backprop and permuted MNIST. So the only difference between this plot and the ones that you saw is this blue line where I'm talking about continual backprop. As we can see that it fully maintains plasticity in the permuted MNIST problem. And this other graph on the right side is a parameter plot for different values of replacement rate. So as I mentioned that we are selectively reinitializing. So replacement rate tells us how many features are we reinitializing. And for example, this replacement rate of 1 E minus 6 corresponds to us replacing 1 millionth of the representation at every time step. And what that means, what that translates to, because we have 2000 features, we would replace 1 unit in every layer after every 500 time steps. So after every 500 updates, we replace just 1 unit. So it's very slow in that way. And as we can also see that the replacement rate is not a very strong parameter. It doesn't affect the performance significantly. Okay, now let's look at the other qualitative measures that Rich talked about for other algorithms and see what continual backprop does. So again, the only difference between this plot and the ones you saw before is the blue line of continual backprop. So if you look at the percentage of dead units, there are almost no dead units. And this is not surprising because the utility measure takes into account the average feature activation. So if a unit is dead, it will be replaced immediately. And there will not be that many dead units. And again, the weight magnitude is small because we are replacing units constantly. So we are getting new units that have smaller weight and magnitude. And finally, the effective rank, which in some sense measures diversity, is also very high. We want this number to be high. And that's, again, not surprising because we are randomly reinitializing units, and random units will have better diversity or better representation, better rank. So we can say that continual backprop solves all the problems that arise because of the loss of plasticity in the MNIST problem. Now we want to see, does it scale to deeper convolutional networks? What happens in the ImageNet problem? And this is the result that we got. This was one of the first plots that Rich showed, where the red line is again the performance of backprop. It's not performing very well. As we can see, the performance dropped significantly after 2000 tasks. L2 and shrink and perturb both help significantly, and they don't lose plasticity after a while. But the performance is still not as good as originally. However, continual backprop does perform very well and almost fully solves the law. It fully maintains plasticity in this ImageNet problem. It gets to around 88, 89% performance finally. But if you look at what was the performance initially, there was not any significant difference between the algorithms. As I mentioned previously, the replacement is fairly slow, so it takes some time for that effect to kick in. And so the performance is improved slowly over time, and it's better. Yeah, now we're done with all of the supervised learning results. And as a cherry on top of the cake, we're gonna present one small reinforcement learning result. So this is an extension to a non-stationary RL problem, which we call slippery AND. It's a standard, it's a small variant of the standard AND problem in PyBullet. And the only difference is that the friction between the ground and the agent is changing after every 10 million time steps. In this case, the agent is rewarded for moving forward. And we have PPO and continual PPO. And continual PPO is based on continual backprop, where you do selective re-initialization. So we can see that PPO performs very well in the beginning, but its performance just collapses completely. L2 and shrink and perturb help a lot, but continual PPO seems to do the best. And it almost fully maintains its plasticity, but not fully. And if you want to look at the behavior of these agents, that's also very intriguing. Like the PPO agent is struggling to walk at all, while continual PPO agent can just run, which is very nice. Okay, now finally moving on to our conclusions. What we have showed is that deep learning networks, which are optimized for one-time learning, you just want to learn once, they totally seem to fail in continual learning. And most of the standard things like normalization and dropout don't seem to help. But we found that simple changes like continual backprop can make them much more effective. We should note that continual backprop has this notion of utility where we rank features, and it's still based on heuristics, and we think there can be much better notions of utility, and it can improve the foundations of this algorithm, especially for the recurrent networks, that things will be much more complicated. This tells us that there is an exciting world for deep networks that can learn continually and that do not lose plasticity. And probably the main beneficiary of this will be the standard reinforcement learning setting, where there are a lot of sources of non-stationarity. For example, standard policy iteration, and even the advanced model-based RL architectures where there are lots of interacting components will benefit from maintaining plasticity. So thank you for your attention, and if you have questions.
Okay, questions? Yeah, can you come to the front?
Yeah, thank you both for the very neat presentation. I think I have a pretty obvious question, which is if you have tried a continual backprop on a single large-scale supervised task like ImageNet, for example, to see if it still works well or perhaps even better.
So I'm guessing you're talking about the stationary setting, and I don't think we have tried in that setting yet. But I think it might improve performance because, as far as I know, it's very common to have a large fraction being dead in large scale networks. So it might improve performance there.
It's a good idea.
Hi, thanks. Yeah, sorry. Thanks for your presentation. I wanted to ask, like, do you make a clear distinction between like improving plasticity and improving transfer? And if you make a distinction, do you think that the improvement of plasticity make a consistent improvement in transfer?
Yeah.
Let me take that one. I would say we're really asking a question that comes before transfer.
Okay, your audio is a bit low. I'm not sure if it is because both of you are not muted.
Wow, let me just try talking closer. Maybe you can hear me?
Yeah.
Good. What was I saying? This question that we're asking comes before that. Like transfer would be you learned on an early task and the transfer lets you do better on a later task. And what our loss of plasticity is the opposite of that. What we learn on the earlier task or what happens on the earlier task makes us do worse on the later task. So I think we have to solve that problem before we can worry about trying to get better from positive transfer.
Okay, so well, maybe I'll do one question from the chat. Okay, there's a question. Thank you for the great talk. It seems that the plasticity gets better with continual backprop, but what about the stability? Does it successfully find a good trade-off sweet spot?
I think that's a good question, and but we have not explored that yet. Like we have not looked at how well we can remember. So it'd be a good direction for future work, but I think it's very well inbuilt in the continual backprop idea, the generate and test idea, where you can, if we have something that's very useful, high utility, we can preserve it. We can stop gradient descent from changing it, and then that way we can maintain stability as well. That's totally unexplored but yet so far.
Yeah, actually, like my question was like in line with the previous question. So it seems like you are focusing one half of the continual learning problem, and in my mind I was thinking, what about the alligator plot? And in the last experiment, like the RL experiment, it showed like there is like the alligator plot phenomena basically, but it keeps the like it keeps going up to the level also. That's why like it maintains plasticity, but like it doesn't solve the stability problem. I do have another question. Is your method like task boundary aware?
Yeah, it's not. We want to develop fully continual methods that don't have this notion of tasks, or even for problems where there are no tasks. Like there is no task boundary.
Okay, and also like, have you studied like combination of what are the nature, like say if you are using dropouts and into regularization together, like all of these methods are independent, like that you can combine both of them and like see how have you studied them, like what are their characteristics?
So far, no, but I think we can infer a lot of things from our previous slides where we have this this graph about what problems, what these methods solve. So maybe it's not clear from this plot which things will help if we combine them together, because they all seem to have different problems. So if we combine L2 with, let's say, I don't know, dropout, it might help, it might have better rank, but those things are not clear. So this can give us a hint for like combining methods that have different strengths might be good.
Okay. Yeah, thanks for the answer and thanks for a great talk.
Okay, so I'm going to do one more question from the chat before we go to the in-person question. So this is a long question, but this is also something that kind of I wanted to ask. So I'll rephrase the question. So the question is, in your MNIST experiments, the network that works for all permitted tasks seems to be the one which classifies an image only based on its pixel histogram, right? Like so, which means that the final network has to be very poor on every task. So what do you think about it? And my question, which is similar to this, is like, do you think permuted MNIST is a good setup to study this problem?
I think permuted MNIST is perfect to study the problem of the loss of plasticity, because we're not concerned with remembering everything. So we're not concerned with how it does in all tasks. The only thing we are concerned about is how it does on the current task. And I'd also add that this is related to this idea of the big world, which means that our agents, our minds are always much smaller than the real world. So we cannot perform well in all cases. So we have to track. So we have to optimize for the situation we are in. We cannot represent the world completely. So obviously we cannot optimize for everything. So we have to do well locally.
Okay, so thank you. I don't know who was first.
Quick question. It's a very quick question. Did you conduct any uncertainty quantification for your experiments when augmenting the number of tasks? It's not just accuracy, but the uncertainty of the model itself.
I think the answer is clearly no. We did not assess the uncertainty. Even our performance measure is a little bit uncertainty oblivious. We're using the argmax of the.
Okay, Rich, your audio is really low. I don't know what changed in the setting. Oh, it might be your.
Let me try this.
Yeah, this is
Can you
much
guys-
better.
Oh, okay, cool. Sorry. I was going to say we don't really are looking at uncertainty, and in fact, we should be paying more attention to it. Note that our performance measure is, we're using the cross entropy loss, but then when reporting results, we're just saying what's the maximum class. We're not really taking even into account if it's predicting things, it should be 0 or giving them non-zero probability. So we could probably do more along those lines. Yeah, and I just want to speak and answer this question and one of the previous questions, that it's really important to do systematic studies, to look at the combinations and look at the parameter settings and explore the whole space. And that's why it's good to have small tasks, and this is relatively small. The slowly changing regression problem is even smaller, and it's been critical for us being able to do systematic tests. It's really important.
Thank you.
Thank you for the fascinating talk, and I hope I understood this correctly. So I see a bit of a maybe circular problem, and that is in the context of, let's say, lifelong learning, these tasks don't have to appear in a frequent fashion where, every 100,000 steps you have the exact same change and so on. However, your hyperparameter for re-initializing the weights is actually always the same, and maybe this should be adaptive. So do you have any thoughts on this?
Well, first I'd like to point out that the algorithms told nothing about the task switches, and it's true also that the task switches are artificial, and in the real case of interest, there are no, they don't happen at regular intervals, and they don't even happen. There's just a gradual concept drifts and changes in the world, and they have all kinds of complicated structure. We need methods that will be able to handle all of that. Now, we would, so the ultimate answer is yes, we would like to automatically set the replacement rate. But it doesn't seem like a really pressing issue at the moment, because we saw that the performance was not very sensitive to it. We can change by an order of magnitude easily without having too big of effect. But in the limit, and I would like to do that. I would really enjoy that meta learning problem of setting the parameters of the algorithm.
Okay, great, thank you.
Thank you very much for a great talk. One thing I was wondering is about, at the beginning we saw several plots with different activation functions, but in this I assume the last experiments were mainly conducted on ReLU-based networks. So I was wondering, because one of the main reasons why we lose plasticity is because of dead neurons, which is an inherent property of ReLUs. And if this is like mitigated if you just use or improve on activation functions like using CoLLAs or other activation functions that are out there, that we kind of, avoid this problem.
So yeah, as we saw that in the regression problem, the issue is not solved by changing the activation functions. And we explored all of these like ELUs and stuff. The simple notion is that all of these activation functions have two different regions, one where there are small gradients, one there are large gradients. So obviously there's always going to be difference. And the way we initialize things currently, we are in the large gradient region. So things change fast, and then eventually they end up in the small gradient range and things change slowly. So as long as we have activation functions with these two things, I don't think just changing the activation function will change things.
Okay, thank you.
Any other questions?
Thanks for the talk. So I was wondering about something from the optimization side of things. So I know you said we don't necessarily know when, there is a concept drift or something in practice, but for the sake of, just knowing, what would happen if, for example, you tried to increase the step size to make up for the increased weights or decrease it, whatever, or if whenever you change the task, you use something other than gradient descent, something like, I don't know, simulated annealing or something like that, like the forbidden methods that maybe might have a use because of the fact that now you might need to jump away, and gradient descent is biasing you towards the previous tasks. And I feel like this is where something like annealing might be more interesting than in the usual machine learning problems.
I think you're suggesting that we should develop special methods that can use information about sort of side channel information about the task having changed.
Yes, more or less, because I'm thinking if those methods work well, then we can worry about detecting changes in task. Like, if such method would work well, then maybe a new problem could be, hey, can we detect concept drifts? And if that's the case, then we apply this kind of methods.
Yeah, I suppose it all depends what you're interested in looking at. But I'm serious about saying we don't, the cases where I'm thinking about, like AI, an agent living in the world, you don't want to be receiving some sort of special side information other than your ordinary input that tells you something special has happened. I guess, maybe you're suggesting we could detect it from our ordinary input, but still,
Yep.
you're putting a lot of structure on the world to say that there's a special thing that happens called concept drift that's different at some time and not at another time. I guess I'd rather have meta learning adapt the parameters, continually, and deciding, how much you should change now and how much you should change later. Yeah, I guess I really feel that strongly because I'm really into the problem of setting the step sizes for different parts of the network and doing that automatically, and that is a meta learning problem. I think that will do a lot, and that'll have a lot to do with because really it's not that the problem has changed now. It's that some part of the problem has changed, other parts remain the same. Maybe your legs are tired today, you need to walk a little bit different, but your arms are fine. Yeah, we want to deal very generally with this problem of how and when you should turn up or turn down the learning in different parts of the network. Thank you for your question.
Thank you.
We are running a bit late. I'm going to ask one last question from the chat. Are there any more questions from the room? Okay, so we'll do. Okay, so if you guys don't mind, so we'll do one remote question and one in person, then we'll conclude. So I'll rephrase the remote question. So, okay, the question is about the capacity of the network. You're trying to maintain plasticity, which is good, right? But when you effectively use all these units by re-initializing them, at some point you're going to run out of capacity, which means you cannot be plastic forever, right? So how would you deal with that?
Shivansh?
Yeah, so I don't see why we would run out of plasticity. You might say we might have to forget things, and that's perfectly fine. Our brains are limited. We have to find out what needs to be remembered, what needs to be forgotten. And again, we are always going to have finite agents in this really big world, so we cannot remember everything we have ever learned, because most of the things might not be useful because the world has changed, so they are no longer useful. So there's always going to be this trade-off between what we want to remember and what we have to forget. And so far we're not focusing on the remembering part, but that needs to be done.
Okay, thank you. Thank you for the talk. So I was thinking, you were not very thorough on how many different utility measurements you tried, but I was wondering if you tried the exact inverse that you did. So meaning, I see it as, why don't we try to spread out the utility across the network instead of, in a way, by ranking the weights and re-initializing them? We are actually doing the opposite in a way. I don't know. I was just wondering your thoughts on that. So spreading the utility across the weights instead of promoting such discrepancy.
So yeah, a couple of things. First, we did not show the results. We do have the results. We did do an ablation study for our utility measure. In fact, it's at the end of the talk, I think. But anyways, your second question, oops, I think I'm out. Your second question was, have we tried to spread the utility? But I think that's not part of the generate and test part, but it's the gradient descent that sets the utility of a unit, not generate and test. Generate and test is just like an addition on top, which finds what are useful units and replaces that.
Yeah, so it was more like, if you actually re-initialize the most useful units, will you be able to actually learn better over time?
So that reminds me of an old paper. What was it? Something about optimal brain surgery. You know, remove things and even important things, and maybe it will make you work better. It is a bit counterintuitive, though, you have to admit.
Yeah, I agree. Okay, thank you.
Thank you.
Okay, so let's thank both Rich and Shibans once again. Okay. I think this concludes the conference.